There are very few options that we have for this particular problem because there are only a few equations relating amplitude differences for damping oscillators. One of the equations that we do see relating amplitude differences in damped oscillators when they oscillate through time is energy. And so the energy equations that we're going to use are E naught equaling to 1 half K A squared and ET equaling to 1 half K x max squared. And you see that they're similar, right? E naught is before any damping occurred. So the A is going to be the amplitude, the full amplitude of the oscillator. But then as time increases or as time goes on, the dampening effects take place, and X max just means how far an oscillator makes it before coming back. And you could probably guess that X max is going to be less than the amplitude after the damping happens through time. So we use this equation to try to relate E of t with E naught, given that X max is going to equal to half of A at time equals 2 minutes or 120 seconds. So let's go ahead and find what ET is with respect to E naught. ET is going to be 1 half K. And now X max is going to be a half of an A. If you take the square of that, that ends up being 1/4 of an A. And I guess then there's a square right there. And if I were to take that 1/4 out in front, and go ahead and say this is now 1 half K squared, this is E naught. So therefore, after a time of 120 seconds, the energy in the system is going to be 1/4 its initial energy. Now, why this is useful is because of the second equation for energy. The second equation for energy comes from this, where it already links energy with respect to time to the initial energy times E, the exponential function, to the power of time divided by tau. And tau is some sort of damping function that's similar to what they're asking for. Tau is equal to m over b. Sorry, I had to look that one up. So tau is equal to m over b, which is something similar to what we need to find here. So finding tau would help us to find that eventually. Let's go ahead and solve for tau. We do this by trying to first get rid of the exponential function. Actually, first we're gonna want to get this in terms of E naught and simplify. And then we want to get rid of the exponential function by taking the natural log of both sides. Let's go ahead and plug in E 1/4 E naught to E sub t, or E of t. 1/4 E naught is equal to E naught exponential negative t over tau. E naughts will cancel out. And what we have is 1/4 is equal to E to the negative t over tau. Okay, now what we're going to do is we're going to take the natural log to try to get rid of the exponential function. Natural log of 1/4 is equal to the natural log of E to the power of negative t over tau. This becomes natural log of 1/4 equaling to just the exponent of this exponential function with that natural log operator. That's going to be a negative t over tau. And that's just a rule of natural logs. They kind of cancel out the effects of the exponential function. So now solving for tau, we got tau equaling to negative t divided by natural log of 1/4. And this ends up being 86.56 seconds. And it's a positive number because this is a negative, but also this becomes a negative. So now we have ourselves a tau. Now, given that tau is equal to m over b, we go ahead and solve for b over 2m. And it so happens that b over 2m is equal to 1 over 2 tau. And finally, that gives us 0.005776 hertz. Okay. So that right there is the damping function. And because it's 1 over a tau, which is in seconds, it will give you a value in hertz. Now for part B, what they want you to find, and they say it in a weird way, they want to know what the factor of the damping frequency is relative to the undamped frequency. So the function is really going to be absolute value of f prime, which is the damped frequency, minus f, which is the undamped frequency, divided by f, the undamped frequency. All right, well, so we don't know f explicitly, but at least we do know omega. And we know omega because it's given as one of the equations for particular damping constants. So I'll show you in just a bit. So what we can do instead is we can just say, instead of finding f prime minus f over f, let's find omega prime minus omega over omega. And we can see that since omega is equal to 2 pi f, the 2 pi's will cancel out across the board. So this is actually going to equal to this because of all the 2 pi's being canceled out. That omega basically equals to f when it's in ratio form. Now the equations is that omega prime is a function of the spring constant, mass, and these damping factors right here. Omega is thus the undamped version, and we pretty much know that from earlier lecture. So to find this, all we need to do is just plug in all these values here. So that function there that we want to find is going to be k over m minus b squared over 4m squared minus k over m, all divided by k over m. Now doing the math, and that is plugging in the k that you have up here, plugging in the m that you have up here, plugging in the ratio b over 2m, and then squaring it that you got right here, you're going to go ahead and get an answer that might shock you. It's 310.7277 minus basically the same number, and it's divided by the same number. And not surprisingly, this will equal to 0. So the answer to this riddle here is that the frequency variation for damped and undamped oscillators is basically negligible. So we'll say that's 0. I'm going to go ahead and show you part A and part B as best as I can. So there you go. And the part that's missing is the K here and this part, but there you go.